Welcome back to our course on compiled construction. After the introduction to lexical analysis using DFAs and regular expressions last time, we are going to take a closer look at lexical analysis, optimizing automata and transforming automata, and also how to use lexical analysis in real-world application using the Lex scanner generator. So today we are taking a closer look at how to transfer the NFAs we've constructed last time to deterministic automata, so NFA to DFA conversion. For this, we have a so-called subset construction algorithm, which finds common states in the NFA, which can actually be joined together in single DFA states. Then we take a look at how to minimize the state space of a DFA, so how to build minimal DFAs using two different approaches. The first one is using Hopcroft's algorithm, the second one is using the Myhill-Nerode method. And finally, we're going to take a look at using scanner generators in the real world, so you don't have to actually do all that stuff by hand, but you can have a program just transforming your input description of your lexical analysis to source code that does this for you. So we'll give examples of Lex syntax and usage, and we'll dig a bit deeper into that because you're going to use this for some practical exercises later on. So what have we achieved so far? We have seen a method to convert such a regular expression like this one here. So we want to recognize all or and, so these two strings, into a non-deterministic finite automaton, so an NFA, and we see that we have a branch here in our graph that detects ALL, so all, and we have the other branch that detects AND, so it detects AND. And this is using the McNaughton, Thompson, and Yamada algorithm to construct this, and you see this is non-deterministic, because in the first state here, the automaton needs to decide when it reads an A, does it need to go to the upper branch here, or can it take the lower branch here? And we have a problem, because if we chose the wrong branch, we'd somehow need to backtrack and go the other way if the second character we read is not the one we would expect on the branch up here. So we have a certain overhead of constructed NFAs. Let's look at a simple example. So we want to recognize strings consisting of an initial A and then an arbitrary sequence of either B or C, which can have arbitrary lengths. So we have the clean star operator here. So it can be 0 or more characters, either B or C. And we've seen, using our construction algorithm, that we start to construct these simple NFAs for detecting these three single characters. So we have an NFA to detect an A, so just starting from S0, reading an A and accepting this, and the same for a B, and another one for the C. So if we construct the NFA for B or C, so the second part in the parentheses here first, we know that we need to start with a new state with epsilon transitions that can go either to the upper branch detecting the B and then using another epsilon transition to our new accepting state S7 here, or it can go to the lower branch using another epsilon transition here, detecting a C, and then going using another epsilon transition to our final accepting state S7. So this is just the part inside of the parentheses, so this is 1B or 1C that is detected. So now we have to construct a bigger automaton to detect the rest of it. So now we want to add the clean star operator. So we want to enable 0 or more iterations of either B or C. And we've seen how to do this. We need to construct a bypass first from a new initial state to the accepting state directly, because we can have 0 characters in our string, so it means we directly go from start to end without consuming any character, and that would be a valid string matching B or C star. If we want to match strings with more, or at least one character, we need to go to the other transition here, and we've already seen this inner construction we've built already, and now we have to enable repetition here. So we can go from S7 to an accepting state. This would mean we read either 1B or 1C, or we can go around here using this new epsilon transition to the start of our previously constructed partial graph to a 6. So for example, we could go here, take the epsilon transition, read a B, go back, read a C, go back, read another C, go back, read another B, and then finally accepting this. And this would be another valid string matching the description B or C clean star. Now, as you see, this looks pretty complex already for this very simple regular expression. And we're not even finished here, because we need to also match the initial A, which always has to be there for a string that matches this regular expression here. So if we want to match A and then a clean star of either B or C, we have to add the recognizer for A in front. So we start now with an initial state as 0, recognize an A, and in this state here, then we can go using an epsilon transition to the state of the partial graph from our previous slide, and this one, as we've seen, detects B or C star. Now, can this be simplified? And if you just used your intuition to build a graph, yes, you'd probably have another idea of building this NFA. And if you look at that one below here, it's probably easy to see that this one fulfills the same conditions. So this detects the same language. So we start with a state as 0, always recognize an A, and then we are in accepting state, which means we only read an A, which is a valid string, or we can go back from S1 to S1 as many times as we want when reading a B or C character. So this reads an A, and then arbitrary many B or Cs, including 0 Bs or Cs after that. That would be much easier. So a good question is, can we somehow get from this complex graph here, which we constructed automatically, so that's something a computer can do easily, obviously, to this graph we constructed using our intuition. So let's see how we can do this. We need to go from an NFA to a DFA to implement the final automaton, because an NFA is not really helpful, because you've seen the implementation of an NFA is not really obvious, because you don't know if you have two choices for the same character, which way to take through your graph. So you need to implement some methods for backtracking, for example, which make your scanner much more complex than needed. We already know that every DFA is also an NFA without the epsilon transitions. And it's also true that we can convert every NFA to an equivalent DFA. We don't want to prove this here. You can prove this by induction. We just show the construction for simplicity. And the method to do this is called a subset construction. So we start with an NFA, which is defined as this 5-tuple here. So we have the set of states Qn. For the NFA states, we have an alphabet sigma. We have our transfer function delta n for our NFA. We have an initial state n0, and we have a set of accepting states fn. And we want to transform this into a deterministic automaton. So this has a set of different states, QD. It has the same alphabet. It has a different transfer or transition function. It has possibly a different start state, and it has a different set of accepting states. So the only thing that actually stays the same is the alphabet. Both automata operate on, and we have to transform the rest. And by doing this, we have to ensure that, of course, the language that's accepted by the DFA we want to construct is equivalent to the language that was accepted by the NFA. So this is our subset construction algorithm here. And the idea of the algorithm is actually to go through the NFA and find sets of states that are equivalent. And they are equivalent because they're connected by epsilon transitions. So you don't need to read any character to move between these states. You can move arbitrarily between these states if they're connected by an epsilon transition. And then we join these states together that are equivalent and build a new DFA which uses these sets of states as a new single state. Because they're equivalent, we don't need to do anything to transfer in our graph between these states. So essentially, we can unify them in one state, and that's the idea behind it. To do this, we first introduce a term which is called the so-called epsilon closure. So an epsilon closure means that you look at a set of states S, and then for this set of states, you look in your graph which of these states in the NFA can be reached from any of the states in S along paths that contain only epsilon transitions. So which of the states can be reached in your NFA from any of the states in S without reading a single character, so just reading an epsilon. And these are identical to a state in S because we can easily just go from one to the other. And this algorithm looks like this. So we start with our start state N0, and we have our state Q0, which is the epsilon closure of our start state N0. So essentially we take a look at, are there any states which are directly reachable using epsilon transitions from our initial state? If so, we add them. If not, well, it's just our initial state, which is the only one. Then we have a set of states Q0, which is initialized with our initial epsilon closure, and we construct a work list which contains Q0 as an element. So this can contain different sets of states. And now we run through a loop. So as long as our work list isn't empty, so as long as we still have work to do, then we remove Q from our work list. So we have in the first iteration our Q0 here, we remove it. And then for each character of the alphabet, so we call this C, which is an element of our alphabet sigma, we calculate the epsilon closure of all the states that can be reached from the state Q we just removed using the character C. So now we take a look at the following states of the current state we're looking at if we are transitioning not using an epsilon transition, but the given character we are iterating over in our for loop here. And we get the epsilon closure of this, so all the states reaching from this reachable from the subsequent state, and copy this into something we call T. And T is then part of our new transfer function, our delta function, going from Q, yes, our state we just removed, to reading our character C. Now, if that T wasn't part of Q0 already, we add T to Q0 and to the work list because we have added something new to our work list here. And if not, we've already seen it, and we go through all of this, so until our work list is empty. So if we have removed the last element here from our work list and we didn't add anything here, then we're actually finished, and we have constructed a new graph with new sets of states, with new sets of start, finite states, and with a new transition function. Now, explaining an algorithm like this just on a slide, well, it's pretty difficult to understand. So what helps here is to take a look at an example. So let's take a look at the constructed grammar for just detecting our string A and then the clean star of B or C, which is shown above here. And we start at our start state, which is here indicated using N0. So that's just a 0 state of our NFA. And so we start with our 3 initial instructions here in our algorithm. So first we take a look at N0 and want to figure out what's the epsilon closure of N0. Now, epsilon closure, as you've seen, means we take a look if are there any epsilon transitions going from N0. No, there's only this one transition, which takes a character, reads a character A. So the epsilon closure of N0 is just N0 itself here. In the second step, we just copy this Q0 to our capital letter Q, D, so it has the same contents, and also add it to our work list. So what we get here is a new transfer function now that starts at a new state. So we go from N0, and we know we read an A, we end up in N1, and we don't know all the other things so far. So now let's go through the loop. So while our work list is not empty, we've seen it wasn't empty because we had N0 as the state in our work list here. We first remove the element from our work list. So we remove N0 from our work list and put it into Q. And then for each character in our alphabet, we go through our for loop here. So we start with the first character, which is an A. And what we do now is we take a look at the epsilon closure of our state Q, so N0, reading the character C. So we're in N0, and now we look at the transition here. So we go to N1, and then we take the epsilon closure of the state we arrived at the end of our delta transition. So we take a look, are there any states that are reachable from N1 using epsilon transitions? And as you can see, from N1 you can go to N2 using an epsilon transition. You can go to N3 using an epsilon transition. Another epsilon transition leads us to N4 or to N6. And we can go even further because we can go using an epsilon transition from N2 also to N9 here. So this set of states, which is reachable from N9, just using epsilon transitions, these are all equivalent. So our element t, our temporary variable keeping this set of states, consists of the state we had looked at before, so the output of delta of q and c, which is N1, and all the states reachable using epsilon transitions, so N2, 3, 4, 6, and 9. So what we do now is we construct a new element of our deterministic transition function here for our state N0 when reading an A. You can end up in N1, N2, N3, N4, N6, or N9. So when you read N0, when you're in N0 and read an A, you can end up here, or you can read epsilons and end up there, or somewhere in between, or even here at the end. What we now do is we add this to the set of our new deterministic states. So we have our initial state N0, and then this set of equivalent states in our non-deterministic automaton here put together as another state, which forms a state in our deterministic automaton. And we add this, because we haven't seen this before, to our work list. Okay, so we are in this while loop, and we ran through our for loop one time because we only looked at what happens in our inner loop when C is A. So we now need to look at the other characters in our input alphabet. Now for B and C, going from N0, well, there's nothing in this automaton, so you don't end up in any subsequent states. So there's nothing happening. Our T is empty. There's no change to Q0. There's no change to the work list. And you can see it in the state diagram of our NFA here in the state table, that there's actually no reachable state if you have a B or a C as an input when you're in N0. So in future iterations, we just skip those which lead to nowhere, so those that don't change Q0. So where are we now? Well, we're once through this for loop and once through the while loop. So essentially we have something new in our work list. And so we end up at the start of our work list again. We have something there. So we now remove the next element from our work list, which is the one we just generated in our previous step. So in 1, 2, 3, 5, 6, 9, these equivalent states here, which all can be reached using epsilon transitions from N1. So now from N1, using non-epsilon transitions, we can actually reach states, well, reading a B up here or reading a C down here. So let's start with a B, because for an A we don't have any valid transitions. So if we read a B, then we have the epsilon closure of the subsequent function, so of our delta function of QC, which is the epsilon closure of our delta function of Q reading a B character, which is the epsilon closure, essentially when we're ending up here, of N5. So now we have the next state reachable when reading a letter, and not only epsilon transitions, which is N5. And now we take a look at the epsilon closure of this state. So from N5, we can go to N8 reading an epsilon, or to N9 reading an epsilon, or we can go back here to N3 reading an epsilon, and then we can read an epsilon here, ending up in N4, or down here, ending up in N6. So we have another joint very big state here. So from n5, well, we're in n5 already, we can reach n6, 9, 3, 5, and 8. So when we're in the state Q, this joint state up here, and read an A, we can actually end up in any of these states listed here, which we just figured out. And what we do now is we add this new joint state again to our list of states for the DFA and add this one to our work list because we haven't seen that one before. So we're again inside of our for loop. We just considered the case up here, reading a B. Now we also need to consider the case down here when reading a C. So we end up in N7, which is essentially the epsilon closure going down here. And then we need to consider the epsilon closure of this state N7, which was reached because we read a C here. And this is, of course, very similar to N5 because we can go here, here, back here, up here, and down here. So this is N7 itself, and the other states we added in the previous step already to the other joint states, so N8, 9, 3, 4, and 6. Again, we add this to our deterministic delta function, so using our new joint state Q here, when reading, sorry, that's a typo, when reading a C, then we end up at this joint state here. We add this one to our set of joint states, and we have this state here in our joint new work list. And now we can go through the other states, and we figure out that no new states are added to Q0 in this and the following iteration. So essentially, we are running to the end of the work list. The work list is empty. So let's see what we actually constructed using this subset construction algorithm. So what we have here now on the left-hand side is our delta function for the non-deterministic automaton, and this one here is the same for our deterministic automaton. So now we have new sets of states, and these sets of states, Q0, 1, 2, 3, they form the new states of our deterministic automaton, and these consist of one or more states of the non-deterministic one. So we start again at a new state D0 here, which is just the old state N0, and we have a transition reading an A. And reading an A, we end up in this new joint state and 1, 2, 3, 4, and so on. Reading a B or a C, well, it doesn't get us anywhere. So this means if you read an A, if you're in N0, you end up either in N1, or you can move on using the epsilons to here, 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 or directly to the end. So this is our joint state. And this joint state forms our new state D1 in our DFA, which is shown here. So from D1, which is already an accepting state, you can reach a B or a C, which would implement these transitions here, including the epsilons, and end up in these two new joint states. And we call these two new joint states in our deterministic automaton D2 and D3. And they can end up in, well, one of the states we've already seen before by reading another B, where we can run up here, or reading another C, we run down here. So this is our deterministic automaton, and this is how we can draw it. So it has three accepting states now, and as you can see, we can start, read an A, and then we can read a B. We can accept it, or we can read arbitrary many B's and still accept it. Or if we read a C, we can still accept it, read arbitrary many C's. We can go back using a B up here, or we can read A and a C, end up here, or we can just read an A and end up in an accepting state. So I think it's pretty obvious that this graph, this deterministic automaton, is identical to this non-deterministic one, and it's quite a bit smaller already. So using this subset construction example, which you could just write down as a piece of source code that implements your set operations and so on, you could actually do this minimization of a graph. But it's not a minimization because we've already seen a simpler solution for this. So what we can achieve now using our subset construction algorithm, we can go from this very complex NFA to detect this regular expression, so strings that match this regular expression, to this less complex deterministic constructed DFA, which is equivalent, so it detects the same language. This is easy to implement, but as you can see, it's still quite a bit bigger than the minimal DFA we got by thinking about the problem for a minute. So, of course, the question is, can we make this even more simple? So, the question is, can we somehow come from this automaton to this automaton, which are, as we've seen, equivalent? So, the problem with this subset construction algorithm is that the DFAs we get out of this algorithm can have a large set of states. This does actually not increase the time needed to scan a string, because you don't need to run through more states in your automaton, but it does increase the size of the recognizer in memory, because obviously the transition table for this graph is bigger than for that one. It doesn't really matter, of course, for these small examples, but if you run scanners for more complex examples, the size of the DFA might be a problem. To be honest, on modern computers for realistic examples, the speed of memory accesses actually often governs the speed of computation. So even though our memory size for storing this delta function is not a real problem anymore, still, if we, for example, can keep our graph or a delta function inside a cache line, we can have a smaller recognizer that actually is faster to execute that stuff. And if you're processing like millions of strings a day using a scanner, for example, you're always compiling lots of stuff, or you're using a scanner in different applications, then it's obvious that a faster scanner is a scanner that is more useful, because you can run more transactions per time unit. So what we want to introduce now is an algorithm to actually minimize this set of states, so to get from the left example to the right example. So the idea behind this is that two states in a DFA are equivalent if it's impossible to tell from the accepting or rejecting behavior of the DFA alone which of these states the DFA currently is in. So for each language, the minimum DFA accepting the language has no equivalent states. So the algorithm by Hopcroft actually works by computing equivalence classes of the states of the unminimized DFA here. So it tries to figure out, are some of these states equivalent? And you might see like D2 and D3, there's some symmetry in there. So maybe some of this might already work out for minimizing it. And the base of this computation is an iteration where in each of the steps we perform, we have a partition of the steps that is coarser than the equivalence. So then equivalent states always belong to the same set of the partition. And if we did this partition here using equivalent states, then we can combine these. So we start with this partitioning here. So we initially partition our automaton in two parts, the ones which consists of accepting states and the ones which consist of non-accepting states, or let's just call them rejecting states, because we need to continue reading some stuff when we're in one of these states. So if our text would end in D0, well, that would not be a valid string. So clearly these are non-equivalent because, well, you need to go on from D0, whereas you can stop in any of these states, D1, D2, and D3. So in our next step, let's assume we have two states Q1 and Q2 in the same set of the current partition. Now, if there is a symbol S, so that we find out that the delta function of the first state, reading a character S, and the delta function of the second state, also reading the same character S, are in different sets of the partition. So when we're in Q1 read S, we end up in a different state than when we're in Q2 and read an S. Then these states are not equivalent, so we need to split the set of states into subsets of equivalent states. So we need to figure out which of these delta functions for Q1 and Q2, given the same character as an input, end up in the same final state. So when step 2 is no longer possible, we have arrived at the true equivalence class. Now, for our very simple example here, actually step 2 was never applicable. So what we find out is we couldn't find anything to split up here because we'd always end up in one of these states here. And this means that all of these states here are actually identical. So D1, D2, and D3 are in one equivalence class, whereas D0 is in the other equivalence class. And so we can now join these states. So D0 is in its own new state S0 here. And the others can be joined into one and the same new state as 1, which is here on the right-hand side. And of course, we have all the transitions in our graph here in this new state S1, going from S1 back to itself when reading either a B or C. So this algorithm can obviously also implement it on a computer, and this helps to minimize all of the states you need to implement your DFA for detecting a certain pattern. So let's look at another example for Hopcroft's algorithm. So here we have a DFA to detect either the string phi or the string phi. So we could write this way using our joint construction here for a DFA. So we start with S0, read an F, and then we either read an E, then we end up here, and then we need to read another E to accept this string, so this would be phi. Or we could read an F, read an I, go down here to S4, and then we need to read another E to end up in S5. Well, an easier way to implement this DFA is shown on the right-hand side here. So we read S0, read an F, then we're in S1, and then we can read either an I or an E to get to a new state S2. So we've renumbered the states. And finally, in both cases, if we read an E as the final character, we end up in our accepting state S3. So S3 and S5, this one and that one down here, seem to, well, obviously, I hope, serve the same purpose because they detect that the string is ended here. So at the steps of our algorithm, we can actually start partitioning this. So we start off with accepting states and non-accepting states here. So we partition our set of states into a set S3, S5, and the set of all the other states 0, 1, 2, and 4. Now, let's see in our next step if we can find equivalences here. So we examine S3 and S5. So S3 and S5 with any character we read, well, ends up in the same situation because we're accepting this. So we don't take any new action here. Then we'll take another look if we take our current partition again here, S3, S5, and the others, the non-accepting states. And then we take a look at the non-accepting states here first, and we read an E. Well, we need to split the set of states. So S2 and S4 are obviously not equivalent because we need an E to go to the one and an I to go to the other. So what we did now here is to split our set, our second partition here of the formerly non-accepting states, into two equivalent sets here. So S0 and S1, and then S2, S4. And then we take a look at S0, S1. We read a character F, so we need to split S1, which means we have this final current partitioning here. So for all characters here, well, we actually end up with all characters here, and we end up accepting this thing. So we have S3, S5 as a beginning here, then S0, S1, and the joint states of S2 and S4.